Afternoon, Shanika. Let's see, well, it could be from, wait, your homework was doing fine. Right? You at least weren't working on mine. Yes. Dr. Rice, did you have something every weekend?
And I finally got
Are they math classes? Oh, okay, I was gonna make you say why you hear that, but. Wait, where the other, so y'all would have intermediate calc 1 with them. What's your other math class with this one?
well, yeah.
Seminar, telling y'all writing the paper right now.
And I couldn't remember. Trying to come to mind. It does have a lot of math. It really does.
The macroeconomics class that I took was essentially, can you understand that a supply curve, that the supply curve can go down, demand curve can go up, and two lines can cross? If you can understand that, you understand half of economics. Change that much?
No.
Yeah, I'm interested to see what math goes in there. Then. It's just like people like to say there's a lot of math counting, but really it's just a credit and debit table. You just make a T-chart. You just add numbers on one side, add numbers on the other, and just make sure the sums are 0 or there's off, you make a note. I always remember people in my classes were struggling with that. I'm just looking at like add 2,000 plus 5,000, you're done. That's it. But I also understand my brain is more thinks more like that in a lot of it. Also unfair Nick comparisons. Because y'all probably figured out, especially if you tutored at all, how you think about mathematics is different than how other people view mathematics. So really you're kind of teaching them style of thinking on top of teaching them the concept itself. And that makes it a lot more difficult. But daily quiz today, center of group G, said all elements in G that what makes the center of a group special? They'll give you one more minute. If you don't need to, because it's kind of when we remember and you don't. Dismissing Shanika. I'll give you 1 minute. Then to get in and type something in. The rest of you have an extra minute now if you want to change things. If you don't know off the top of your head, the answer, at least give me a wrong answer. It's better than no. All right, I'm gonna watch answers in 10 seconds. What was answers come in? 5, 4, 3, 2, and 1. Lucky answers. Wow. What is so special about the center of a group? Yeah, it's a set of all elements in G that commutes with all the elements in G. Let's put that in the screen share prepared so I can hop right to it in our notes. There it is. Because we don't have commutativity as a given inside the group, so it's still a desired property, right? It's in part just because what we're so used to working with it. We still like to then say, okay, well, what elements can we have that commute with everything else? So if we go back to D4, we're going to see that there are some elements that are in the center. What is one element that is always guaranteed to be in the center? And the identity element is one element that commutes with everything that's in part based on its definition, right? You have to be able to multiply by the identity element on the left and the right and not change that value. So he said, all right, one of the things we're going to prove is that the center of a group forms a subgroup inside of that group. So we're just going to apply the one-step subgroup test, and we know we can because we know the center is not empty, because again, what's in the center always?
Identity.
Yeah, the identity, right? So we started talking about, all right, for the one-step subgroup test, we said, all right, I need to be able to choose any two elements from the center of G and show the first element times inverse of the second element is also in that same set. So really I need to show A times B inverse commutes with any other element inside the group G. Well, we said, if I'm choosing A from here, I know A is going to commute, okay? But what's the one thing that's currently stuck? And I'm not able to move it all. If I look at A times B inverse times X. What's the one thing I can't commute? B inverse. Okay. I know B is in the center, so I know B will commute with anything, but what about B inverse? So the question we're going to answer and be able to show is that the inverse, if B is in there, its inverse is also. That's going to be true for any of them. So
now earlier we said you're taking E. So it's A and B or just one of those elements?
Technically the second one could be true because we know E is in the set, but A and B is just some general element. We're guaranteed the identity element in there, so there's always a possibility that you could actually choose when you're choosing the general elements A and B, but A and B are nothing that particular. All right, well, going back to our argument, so we're going to get a thought process down. Since B is in the center of G, we know that for any, next element of G, we can look at the following. Consider B inverse times X. And since X is any element in G, as long as I can figure out a way to move that inverse to the other side without ever applying commutativity, I can confirm that the inverse of B will be with any elements. Well, how can I make a B appear? Because I probably want to get rid of that B inverse on the left hand side. Ooh, great idea, but do I have an equation yet? No, I just have an expression, right? So I don't have this concept that I can multiply like the left and right hand side. But there is one thing I can multiply by that will never change the expression. And then the element. So I gotta figure out, okay, do I want to multiply by my identity element on the left hand side and right hand side? It really doesn't matter too much. So which one do you want to do? Left hand side. So
Wait, question, how you say it don't matter, but, like. Yeah, so I thought you said that we have to not do it coming in.
So I can't do anything with B inverse being communicated, because that's what we're trying to show. But you're gonna see the inverse X. All I'm doing is multiplying on the left by an identity element, which I know this is true based on property of identity. Technically, B inverse is in my group, X is in the group, and you know my identity element is in the center. So I know my identity element can use with anything, so I can move that around. Particularly. Right? It doesn't matter whether or not I put multiplication by my identity element in the middle or even on the far right. That's what I was trying to say. But it's only for that one. All right, well, how can I rewrite the identity? So do I want to do B times B inverse, or do I want to do B inverse times B? Well, we can try it all out, right? If we're ever unsure, just like if we have an algebra class, right? You need to do a calculation on pen and paper real quick. No issue. So let's just experiment. So green is just more experimenting and multiplying the left by my identity element. And I say B inverse X. I can still make an argument with it.
Wait. Oh, never mind.
No, there you go. The stuff can be confusing, so never hesitate to ask for clarification.
Now we should do it in the middle. We should put me in the middle.
Okay. So if I do B in the middle, what do you mean in the middle? It's like in between the two B inverses? Or what?
Never mind, I was gonna say, if we put in the middle, then we would get B inverse, B inverse, but then that's just make it our next B inverse.
Yeah. Yeah. So I'm starting to see that, okay, if I multiply on the left by the identity element, I'm still gonna end up with a B inverse stuck on the left. Then what's my other option to try? Multiply it on the right. So if I consider B inverse times X times the identity element, again, I can do the same concept. Well, how can I rewrite the identity element? Inverse. This is happening because the identity elements. And, oh, just T. So B inverse X. B inverse. We're just applying the definition of the inverse and then we're in a group. So B times its inverse would make that identity element appear. Ooh, wait a second. What can I do here? Well, there's no factor, but I get it. There's not really a factor here because we don't have distributed property. But at least we feel like maybe we're in the right direction. Can I get a B inverse to appear on the right hand side of the X? Yeah. Yeah, and that's what I want to show that B inverse is commutative. What do I know about the element B? It is commutative with anything, because what set is B coming from? G. It's not just G. So you're absolutely correct saying G, but I can be more particular. Coming from the center of my group. I said let B be in the center of my group. And if it's in the center of my group, that means it commutes with any element of my group, including this frame of X that we chose. So because That element B is in the center of my group G. I can commute this x times b multiplication and turn it into a b times x. And now what do I have on the left hand side of that expression?
B inverse.
B inverse
Okay.
times
I didn't think of-
B inverse times or B inverse times B. And anything times its inverse becomes and there we go. Oops, I forgot my negative one, that'd be confusing otherwise. And then I take the identity element, multiply it by anything. Or get that anything back. And what have we effectively shown about the inverse of B? Is also commutative. Because B is commutative, its inverse is also commutative. Therefore, B inverse x is equal to x inverse for all x in my group. Means that the inverse is also in the center of G. It's kind of like this little lemma that we have to prove in the middle of our main. And then still, I don't remember my overall goal. What are we trying to show about the center of the group G?
That B is in it, B inverse.
So that's what we were showing there in this little plot. Absolutely.
Oh, the center.
What was my main statement?
A times B inverse.
Yes, because we're trying to apply the one set subgroup test to show that the center of the group is a subgroup.
The center of group is a subgroup.
And to show that this anything to subgroup, we're applying the one-step subgroup test, which is why we need to investigate what the inverse is. Where is the inverse? What does it do? Well, now that we know that both B and its inverse are in the center of G. Yeah. So I'm going to say we, since that, then for any x, an element of G, as an element of G. If I do AB inverse times that element x, because B inverse is in the center, I can do what the inverse in x terms. I can do it. This is the same thing that is A times X times the inverse. Because we showed B inverse is in the center. And what else can I do with A? I can move it as well, because it's also in the center. This is X times A times B inverse. Which means that multiplication, A times B inverse, commutes with any element X. So therefore, AB inverse times an element X is equal to X times AB inverse for all X in my group, which means that that term AB inverse belongs to what set? AB inverse would be an element of my group. And I just showed that it commutes with any other element of my group. So beware. In the center of G. So we've taken any two elements, A and B, from the center of G, and we are able to show that A times the inverse of the first element times the inverse of the second element also in that set. Therefore, by the one-step subgroup test, what do we have?
Just needed the center and the.
That and then when we're done with the proof, what do we always put? Yeah, that's what we like square. Which is also kind of a cool thing, because then what it tells us is our groups of dealing. Well, what do I know about the center of that group?
Subset of the group.
But technically it's a subset because of how relaxed the subset definition would be, but I think it's what you're picking up on. The abelian, it's a center. Yeah. So we kind of get this fun little corollary. So G is an abelian group. And the center of G is the group. We make fun little observations there. And we can also change our concentration. So whether or not we're looking at a particular set of elements that commute with everything in the group, we can also say, okay, well, if I choose a particular element from my group, what are the things that actually commute with that? But first off, I guess you're gonna see me scroll up, so I'm gonna go get our Cayley table. With that one. For that dihedral group of order H. See how long it's been? This is also part of the reason why I made us go through and write out that entire table. So now we can keep referencing it. So what is the center? Of the dihedral group of order H. So I need to figure out what elements or elements in this group to purple or blue. Purple. We can write our answer up here. I want to figure out what element will commute with every other element in D4. Well, I kind of get one for free, and what is that? Okay, and the element, which for this particular group is. Question is there anything else that commutes with every other element? And as long as you can find it as something like, let's say, R270, as long as you can find something that it doesn't commute with, then it can't be in the set, right? The counter for all elements is need to find one case for this part, and then for all statements of default. Does anyone see? What about R90? What's your count? It's true. What's count?
like not R90.
Like,
If you do R90 and R90, you don't get R90. You get R180.
so it's not about the end, well, it is somewhat about the end result, but remember, we're testing for commutativity. Right, can R90 commute with every other element in the group? So if I consider R90, R90, I commute that, just R90, R90, that one can stay the same. But can you find something like, let's say, R90 composed with the horizontal flip? What was its result? D2. Should be D2. Based on our table. And then what about horizontal flip composed with R90? So I commute that operation and flip the order. Yeah, when I do that, it's D1. So maybe you use X numbers to go back to this stuff. But mainly the point is, did it matter which way I operated these two elements together? Good. Yeah, so they don't commute with each other. So I already get what two elements can't be in my set.
R90 and H.
H and R9, both of them. All right, what are some other options? R180. Look at what happens with R180. R180 composed with R0, simple. R180 composed with R90 gives me R270. And if I do R90 composed with R180, let's look at R270. So that commutes. 180 with itself will commute because any element will commute with itself. What about R180 with R270? So 180, 270 is R90, and then I go 270, 180. That's also still R90. So those are good. What about rotation of 180 degrees of the horizontal flip? That gives me vertical flip. Then I do horizontal flip with rotation of 180 degrees. That also gives me a vertical flip. And if you do this with both the vertical flips, so compose R180 with your vertical flip or your two diagonal flips, you'll see that R180, so rotating by 180 degrees, commutes with every other element. R270 volts. You can also pick a particular choice. So what happens when I do R270 composed with V? What's my result? 2. And then what is V composed with R270? 1. So do the vertical flip and the rotation by 270 degrees. Does it commute with everything? They don't commute with each other. Then technically I have to look at D1 and D2, but I don't even think D1 and D2 commute with each other. Do they? No, they do. They both give you R180. You'd be able to pick, another element to show like 90 rotation by 90. And you can show that both of those won't commute with R90. So then we get the centralizer. The negative group of 1 or 8. The elements that commute with any other elements are just the element of no rotation, but also rotation by 180 degrees. What questions do you have that? Right now. Anyone back there tonight? Usually it's normal Mondays. They don't have AC on Monday. So let's go back And go to that question that I posed earlier. The centralizer says what elements commute with every other element of the group. I can ask a slightly different question. If I take a particular element from my group, what are all the things that commute with it? So like, for example, we know R90 and the horizontal flip don't commute with each other, but maybe R90 and a vertical flip, do, or maybe R90 and the first diagonal flip, do, right? So it could also be of interest to start studying what things will actually commute with R90, or what things will actually commute with R270, or a vertical flip, or my diagonal, one of my two diagonals. So we change our perspective like that, we define a new set. Something called the centralizer of a sheet. In A, this lowercase a is representing a particular element. Don't we use a little different letter than the lowercase a? What do you want? B? All right. That's the fun thing about definitions. You can change that into variable you want to, for the most part. So we're going to let B be an element of our group. The centralizer of B in G is the set of all elements in G that commutes with the element that we chose, that little b. That is, if we do this with set notation, we're going to do capital C of that lowercase b, so centralizer of b. It's kind of what we're trying to portray with that. And it's going to be a set of all elements in my group, such that x times b is equal to b times x. Or you could also say that it commutes. So by definition, the centralizer in the center. So centralizer of elements and the center of the group are technically two different sets, so they may have a lot of overlap and maybe specific instances where they can be the same, depending on what that element is that you choose. And one of the things you're going to show in your homework is that the centralizer of an element also forms a subgroup. So it still acts as a group. Actually, we can, no, I want to come back down to it. We can finish running, sorry. But just verify as well, I meant to do this maybe a second ago, that just that set of two elements, so rotation of 0 degrees and rotation of 180 degrees, just verify that it's a group real quick. Well, function composition is associative, all right, so we got that. Do I have an identity element in that set? Yeah, my identity element was R0. And then does everything in that set have an inverse? Yeah, identity elements its own inverse, and what happens when I commute R180 with itself? It's my identity element. So R180 is also its own inverse. So it's associative, There's an identity element, everything in there has an inverse, so what can we call it? Group. But it still holds those properties, again, that's the power that one step subgroup has. It still verifies all of that, but we get a lot for free because we know we're already existing inside of a group. All right, I'm gonna have to do a little bit of scrolling up and down. I want us to find the centralizer of the horizontal flip. So that horizontal flip is coming from that dihedral group of order 8, i.e. the symmetries of a square. So if I want to just make sure that I understand this, the centralizer of the horizontal flip is going to be all elements that I can choose from my dihedral group of order 8, such that it commutes with that horizontal flip. So I got to go back to my Cayley dating. And what elements commute?
Geo.
Yeah, my identity element's definitely going to commute with it. Whoops, not part 10. What up? Well, you know one for free already as well.
R180.
R180, but then I'll scroll back up. Why was I guaranteed that R0 and R180 will commute with H? Because they're in the center of the same group. And I just got to see, all right, well, if I focus in on, let's do a highlight. What can I highlight with? Y'all okay if I use orange or yellow? Which one though? Let me ask. Yellow is good. So we already know, like orange, the ones we know that H commutes to R180 and R0. Are there any other elements that it commutes with? Vertical flip. So if I do horizontal flip with a vertical flip, it's R180. If I do a vertical flip with a horizontal flip, it's also R180. So I know vertical flip is in there. Is there anything else? Which one? Yeah, it commutes with itself. So the horizontal flip with a horizontal flip gives me R0. And if I flip the order, and I do a horizontal flip with a horizontal flip, it's still going to give me R0. Is there any other elements? I'm going to go add H to our set. Can you see anything else over here? So if I do a horizontal flip with D1 first, I get R270. But if I do horizontal flip and then D1, I get R90. And similar story if I do it with D2. So it does not commute with D1 or D2. We'll get rid of this orange highlights thing so we don't mix them up.
So how many do you got out of this? 2 of them or 3? Okay.
They actually have 4 elements for the centralizer of H.
I assume they'd be the same because it was so before, but it's not.
As far as I'm aware, there's no pattern of that. As far as I'm aware, there might be certain instances where you can start starting patterns like that. And that's part of what all of this is we're going to discern patterns when I'm only given, I have associativity, I have an identity element, and everything is inverses. What about so I don't want to be writing in purple yet. What about the centralizer for R90?
Do have all the things from H then. And then more stuff.
Careful. Here, let me It's the other one's already getting a little crazy. I'll paste it again down here. So now I'm looking for this set of all elements in D4 such that R90 commutes with those elements. Then I go back through and say what commutes. So what were you saying first?
Why do they have like the stuff from H and then more things like that? If
Well-
Cause you said, cause we did this thing with the H and then the other one before it, because they were in the center of the same group.
Yeah, so it still contain R0 and R180, right? R90 will, middle of the last 10 per second commute with R, what did I just say? I don't even know. R90 will commute with R0 and R180 because of that proper, what you were noticing in that R0 and R180 are in the center of this. So yeah, we know we're guaranteed these two elements. That's absolutely correct. Question is there anything else? I can use R270. If I do R90 operating with R270, I get my identity moment. And R270 commuted with R90, also get my identity moment. I get that for free because it's an inverse. That's part of the reason why H is also. The R270 is in there. Because it's going to commute with R90. Is there anything else that commutes with R90? Yeah, it'll commute with itself. Is there anything else?
We don't know.
Yeah, R0 is there.
I'm confused.
Okay.
But why is it? Now we know, we already, the first one you put down the R zero and R180.
Mhm.
Why did we not automatically know to put down the NH, so we need to automatically put down? I understand the R0 part, but the R180, how did we know to put that down first as well?
So what was the center of this diagonal group of order?
On the R0 and the R180.
Yeah. Which means we know that R0 and R180 commute with what other element of my group? All of them, right? That was one of the special things about being in the center. It commutes with every. Which means it's going to commute with R0. They're going to commute with R90. They're going to commute with R180. They're going to commute with R270, H, B, D1, D2. So we're saying we look in at a particular element. So like down here, as we're saying, now we're looking at just R90. And I need to figure out what commutes with R90. Well, because R0 and R180 are in the center, we know they commute with R90. So that's why in both cases we're just like, okay, well, we already know that, we know that's going to be intercentralized. But then I have to figure out, is there anything else? So there might be particular elements that commute with this, but not with others. Feel better?
Yeah.
Yeah, good. Yeah, you can ask questions. That's for all of them. All right, we know R0, R180, R270, R90 will be in the centralizer of R. Is there anything else? What about my vertical horizontal flip? You know, either my diagonal flips. We'll see that the order in which I do those operations will matter. So it just ends up being those four elements.
If you clarify, you got the last two elements, it's R270 and it's R90.
I just looked at, well, first off, R90 and R270 are inverses of each other, right? So it doesn't matter what order I commute or operate those two in, they're both going to come out to do the same element, which is my identity. So that's how I know R70 commutes with R90. And then any element can commute with itself. A times A is the same thing as A times A, or R90 times R90 is the same thing as R90 times R90. What other questions I got? Next up, kind of actually shows up in that centralizer of R90. And it's in part because my rotations are special. Oh, we already showed that all of my rotations form a subgroup inside the dihedral group of order H. So I just consider those rotations. But how can I get the concept of 180 groups? I can break it down into two instances of one operation. Or 90. If I rotate by 90 degrees and then rotate by 90 degrees again, I just get my 180-degree rotation. What about the 270-degree rotation? I can just rotate 3 times, right? Or by 90 degrees. 90 degrees plus 90 degrees plus 90 degrees, that's what gave me 270. And how can I generate that identity element R0 just through 90-degree rotations? Kind of do 4 90-degree rotations, which give me 360, which would be the equivalent of rotating that. So really, even though, and even in the centralizer, I'm viewing 4 specific elements, 3 of those can just be created by taking one of them and operating it with itself. So we're going to start investigating that as well. So we get 2 definitions of what it means to be an order. And this is in part where the order, dihedral group of order 8, how we keep hearing that order term come in. Well, how many elements are in D4? There's 8. That's where it's coming from. So the number of elements in a group is called its order. We'll see why it's different in cardinality. But we will hijack that cardinality notation and say, I'm taking the absolute value of my group that's referring to its order. So the dihedral group of order 8 has order 8 because there's 8 elements in that group. Now there's symmetries of a square. What about the symmetries of a triangle? I don't remember how many symmetries we have for a triangle. There's 6. There's 3 rotations and 3 flips. Depending on how much you want to rotate, you could rotate a triangle 3 times before you got all the way back. And then you had 3 flips across each corner of the triangle.
So it wouldn't be D3?
No, D3, yes. Sorry. Thank you. I mean, yes, I was testing. Good job, you passed. And we can already see the pattern probably. Yeah. So looking at symmetries of all pentagons. Yes, I got my polygons corrected, D10, and in general. Group of symmetries of an n-gon has 2 times n elements. What about Z5? What is the order of Z5? You showed it was a group under addition. Oh, it would be 4. Well, I'm gonna turn Z5. I'm not putting that little circle with the cross through it. On the superscript, so it'd be 5, it'd be 0, 1, 2, 3, and 4. So you need 5 elements.
So where's the 0 now?
It's always defined to be with 0.
Because where the plus is.
Yeah. Or that ZN with cross, that extra subscript. It said start at 1. Down up, which means, I guess while we're here, we're about out of time and I don't have time to go to the next concept. So if I did, when I come in like defer to Z5 cross, what's its cardinality? 54. So the order of a group that I can make on that set would be 4. There's 4 elements to it. And on Wednesday, we're going to come in and we're going to find what needs to be an order of an element. Not an order of a group, an order of an element. Okay, so let's see. I want to get you all one more homework assignment. That'll probably be due next Wednesday. Just before your test. That way we can more feedback on some of this stuff, and then we can be a little bit more prepared for the test. All right.
Next Friday.
Next Friday, October 6th. Right?
I didn't hear October 6th.
Yep, October 6th. That's when the midterm is going to be.
Okay. I had one quick question.